Right, my name is Nitsan. I'm going to talk to you about FlameGraphs and how we can use them to visualize profiles and what comes up when we use FlameGraphs in Java and Perf. So this is the optimistic we love FlameGraphs slide. There's the less optimistic version where stuff doesn't work out, but I've never resorted to emulation yet, so it should be okay. This is a funny leg. Anyway, I do consulting now, so I do performance engineering consulting. I write a blog. Does anybody read the blog? Wow, all of you, like 5 people, great. And I contribute to some open source projects. Notably for this talk, the relevant parts are Honest Profiler and Perf-map-agent. And I organize the Cape Town Jug. I live in Cape Town, so if you are in Cape Town and you want to give a talk or come to one of our meetups, give me a call. Right, we live in a lovely industry where we can answer this question. So what is the root of all evil? It's not Marxism, it's not capitalism, it's not consumerism, and it's not child labor. We know what the root of all evil is. And the root of all evil is premature optimization, because premature anything is bad. But I think of this quote, the important thing is that most of the time, small efficiencies don't matter, and we shouldn't focus on them, right? Because if we do, we'll write bad code that nobody understands. What it doesn't answer is when is a good time to optimize, and what should I optimize? And often with performance, the problem is not the problem. The problem that the user reports is not directly relatable to a problem as seen on your system, and from that, deducting what the problem is actually in your code is often troublesome. If you start from scratch every time, you'll take a very long time solving problems. So what we should do is start with requirements. If you've been to Monica's talk on the first day of the conference, then you know the process that you should take to find performance issues and modeling your performance process. But you have to start with some requirement. If you just want it to go fast, that doesn't mean anything. You want it to go fast in a particular way. How many requests per second? How many milliseconds to respond to a request, and so on. So you need to get requirements, you need to measure to those requirements, and then if you're not happy with what you found, then you profile. Yeah, there's a few more steps of diagnosing that the problem is CPU bound, and there is something to look at in a CPU profiler. Ultimately, you go down the rabbit hole of profiling, you find the issue in a profile, and then you try and optimize it. And when you think you've solved it, you measure again. And this is very important because people don't do this. They solve the problem in their heads, and then they think they're done. They don't measure again. They re-release their product, and they haven't solved anything. So measure after you fix, very important. Right, who knows Java? It's more like, are you awake kind of thing. Great, everybody knows Java. Who knows what FlameGraphs are? Great. Who knows Perf, Linux Perf in particular? Good. It's actually a good portion. Right, so we're going to talk about these tools combined. This is Brendan Gregg. He's the inventor of FlameGraphs. The important thing about Brendan Gregg, I don't think I've ever seen him this big. But the important thing about him is that he works for Netflix. He used to work for Joey, and this guy solves a lot of performance issues on large scales, a lot of applications he needs to look at, and he wants a good tool to look at profiles and to diagnose performance issues, and FlameGraphs are his way to do his job. And this is what he has to say about them. FlameGraphs are a visualization of profile software, allowing the most frequent code path to be identified quickly and accurately. Well, he would say that, because it's his baby, right? This is what FlameGraphs look like. And it's a lovely screen to see FlameGraphs on, because it's huge. But despite the fact that they're very attractive, you don't know what they mean without spending some time with them, which is exactly what we'll do. So how does this game work? We take inputs from sampling profilers. Sampling profilers all work relatively the same. You collect some stacks. I hope everybody knows what a call stack looks like. One method calls the other, calls the other. It's what you get from print stack trace, commonly. You collect X samples per second, so maybe you collect 1,000 samples per second, maybe 100, maybe 10, depending on the overhead that your profiler has, or depending on how frequent you want to sample, but you pick a frequency, and then you have to present the data. It's a lot of data, because if you've collected 10,000 samples, you're not just going to read through them manually. So we end up with 3 common visualization techniques. There's the flat view, which gives you the hot method. It's the hot method list. And then, hash map get is at the top, and you wonder what you could replace hash map get with, maybe. The problem with the flat view is that often you don't get context with that method name. So I tell you it's hash map get, but in the whole of your application, hash map get is used in millions of places, and now you need to go and find what's the relevant call site. And this is typically done with something called a tree view. And in a tree view, which anybody who's ever used a profiler is familiar with, you click your way into many, many depth of frames until you find eventually the hotspot. It's a very clickety way of looking through data. And then we have FlameGraphs, which we'll expand on. So flat view looks like this. This is from Java Mission Control. This is what the tree view looks like. And the problem I find with tree view, and I resent that because I have to use profilers quite a lot, is that it fills up the screen very, very quickly. Java methods are very, very verbosely named. Class names are very long. And very quickly you run out of your width. And then the stacks are also very deep in Java because layers upon layers of abstraction. You use Spring, you use Netty, you use whatever framework. At the end of the day, this could be hundreds of methods deep. But if you're starting to dig through, very quickly you lose the whole picture. You don't know where you came from, and you have to juggle in your mind which hotspot is this compared to the rest of the profile. So they very quickly help you lose your way. And FlameGraphs do 2 things, in my opinion, which is not like an expert UI person, but for one thing, they use your assets well. They give you a lot of width for method names and so on. And they give you a big picture of the system to look at. And the last thing is they appeal to your ability to look at pictures and diagnose patterns as a human being, whereas a tree always looks like a tree with lots of clickety crosses on it. So how do you get a flame graph? Because they're so attractive. You use your profiler, you collect stacks in whichever format, a JFR file, 8-prof file. If you use Honest Profile, it's got its own binary format. You convert the stack traces into something called collapsed stacks, which is sort of a uniform format we'll have a look at. Importantly, it's a very simple text representation. So you can very easily take that text file and manipulate it, change it, use grep to only get the parts of the profile you care about, or change names around so they make more sense, add some prefixes, whatever. You can play with this very easily, so you can build tools to add to this tool chain. And then from the collapse stacks, you go into the FlameGraph script, which is a Perl script, which produces an SVG, which is also quite a simple format, but importantly, it's a text transformation in a Perl script that's like 500 lines. So does anybody know Perl? Right. Yeah, I had a look at it and learned it in an afternoon. It's a very simple language. I can't claim to know it well, but it's a very small little script. And what that means is that as opposed to, say, Java Mission Control or JVisual VM, where to change anything is this big endeavor and dig through UI code that is usually quite hard to negotiate, this is a fairly simple script. You can get in there, you can change things. And I've done just that, and it's really quite simple. So recommended hacking. So at the end of it all, we end up with this flame graphs, which I've shown 3 times by now, so I hope you understand it. But maybe you don't. Maybe you don't understand it because I haven't actually explained anything about it. So what does it all mean? This is like the textbook definition of it. So read through it. The depth is expressed in the height of the flame graph. The width is the number of samples. So if a frame is very, very wide, that means lots of samples collected there. And typically the roots are very, very wide because that's where all the stacks start. Importantly, the width is the total time. It's not the self time. The more traditional profile, you have a differentiation between the two. Here, the width of the frame is the total time. The color will change depending on what you decide it should mean, and we'll have a look at what it turns out to be for us. So I'm going to have to switch to the browser because it doesn't actually work in my presentation tool of choice, or any other actually that I've tried. This is what the collapsed stack formats look like. You have a chain of methods, delimited by semicolons. Very simple. At the end, you have a space and the number of collected stacks. And we push this through the FlameGraph script, and we get this, which is not that exciting, right? It's one sample. It fills up the whole graph, so we can zoom in and out to our heart's content, and we can get all these sort of nice hover sort of things. But ultimately, it's one sample. That's not science, right? We need lots of samples. So if we had 1 million samples, it would look exactly the same because it's exactly the same profile. Everything collected in the same place, it doesn't change anything. If we have different sample rates in different places, they will change the width because the ratios is maintained, everything is in one place. We just get to see that there's 1 million samples. Okay, so this is a slightly more interesting but still very synthetic profile, right? Where all the stacks start at method 5, and the calls up to that method, and then we have 6, 7, 8, 9, and this is going to look obviously different than before. We're going to end up with something like this. The reason I'm showing this is to give you a bit of an intuition about what these things end up looking, where they come from. Importantly, here we can see that while it's very easy to see the width of the top frames, the self-time for anything below that is you calculate it from deducting one from the other. So while 5 only had one sample attached to it, because it's in all the other stacks, we get all the samples collected in its total time. Finally, this is like a slightly more complex and still synthetic collection. What we see here is that the frames are sorted alphabetically. The x-axis doesn't have any relation to time. Okay, it's not that method A happened before method B. We just order them this way to have a stable picture when we look at it. So if the profile changes, we move from a familiar picture to another picture. This works well in most cases. We also get a little bit of tooling here where we can search for a method, let's say 7, and get an idea of how much of the profile it actually shows up in. In a synthetic profile, that's not really very important, but in a more complex one, which we'll move to, it will become more important. So, what can we feed to the beast? What sort of flame graphs can we see? We can get inputs from lots of different profilers. This is a survey by JRebel about which tools people use. These tools split into 2 camps, roughly. There's the JVisualVM camp, which is most of the commercial products. And the reason they all share the same API is because it's the official API. They all use the SafePoint biased yet generally available way of collecting samples. The problem with SafePoint bias is that there's only so much you can see. You can only see the JVM at safe points. Anybody knows what a safe point is? Yeah, okay. Generally, Java developers are not aware of safe points. Safe points are places in your program where the JVM can stop your thread. JVM threads voluntary stop. You can't just interrupt them and know what their state is. So to get the stack, to walk the stack, you have to stop at a safe point, or is that, at least that's the traditional way of doing it. And every time you collect a sample, they will typically pause all the threads in your application and collect a sample from all of them. So it's a stop-the-world pause. Not only it's stop-the-world pause, it's also unbounded in length, because it's going to take longer if you have more threads. And part of the problem is you sample the blocked threads as well as the running threads. So let's say I have a worker pool with a bazillion threads in waiting to be used. I'm going to have to walk through all of them and find where they're blocked, which is going to take time. But you can use it if you like. So you don't have to, but it's generally not recommended because it comes with the provisos above. But it does work on every JVM. The next one up is Java Mission Control and Honest Profiler, which use something called async at call trace. There's another one from Google, which I forget its name, but it's a very similar mechanism. They don't have a safe point bias. They use an internal mechanism to collect the stack at an interrupt. So you interrupt a running thread, and you collect its stack. That's great. It's still only going to give you the Java stack. And because of implementation issues, basically, there's some bits of the runtime that are hidden from it. In particular, and most importantly, the generated runtime stubs for a lot of special methods in the JDK, which I have to explain really. When you use system array copy, it's not a normal method. It's marked as a native method, but if you looked at the actual mechanics of the JVM, you'll find that it's actually replaced with another method. It's an intrinsic, and therefore the native call is gone. It's not a JNI call. It's an internal call to a generated method that is very specialized and very efficient. The reason that the JDK developers spend so much time on this is to make it efficient, right? So by extension, they made it efficient because it was important. You should see it in profiles. The reason you've never seen system array copy in your profiler is because you can't see it. There's no save point in it, so a traditional profiler won't show it to you. And the stack is not walkable because of reasons. So you end up not seeing it in Java Mission Control either. A typical application should see a little bit of array copy, but you never see it. So it's a funny situation where you've hidden away the common hotspots by optimizing them. Okay, so Java profilers typically care about only Java code, only some of the time. They have their failures, but most of the time, they work every time, right? The reality is quite different. The reality is that when you run your Java applications, you typically use a bit of OS code. You use some JVM runtime code. It has to collect your garbage. It has to compile. You use some runtime stubs. You call into the JNI methods that come with the JDK, and you also call into your own native libraries. Now, sometimes you call into their methods. Sometimes they start background threads that do things, like a messaging library that would have a background thread that reads from your network card, right? You're not going to see that thread eating CPU in your Java profiler. And then there's your code. The reason there's a question mark on that is because your code doesn't actually run. Your code is written in Java. Very few people actually write bytecode. You compile it to bytecode. It may have been Java or Scala or anything to begin with. And then the bytecode goes into the interpreter. The interpreter runs the typically cold code in your application until it's considered hot enough to be compiled. And compilation is now tiered, so the world is a bit more complicated. But basically, you have your client compiler on one end, the server compiler on the other end, and a transition chain between the two places. An important distinction is that as part of the optimization of your code, a lot of code gets inlined. And we'll see why that's important in a second. Okay, so that's the real world. We profile it using a system profiler, which is Perf. It's the Linux system profiler, so it should be available on most systems. It can profile the user space and kernel programs, and it's a standard tool. And now it works with Java. If you look it up on Stack Overflow, there's maybe all the questions or all the data about how it doesn't work, or it takes a bit of hacking to make it work. It now pretty much works with Java. And lots of people were involved. It's actually quite a nice community effort around making this happen. I was involved a little bit. I think the main contributors here are Jonas and Brendan Gregg, who went and wrote a patch, and OpenJDK team actually implemented it properly, and it's all great now. So, some assembly is required, so you don't have to read the slide, but if you get the slide deck later, you'll know what you need to get this going, and the blog post at the bottom goes into a bit more detail about how to get this done. So, what do we get after we've gone through all this effort of installing this and building this and all this crap? What do we get out of it? We get a full stack for our applications. We can see everything suddenly. Okay, we can use a lot of perf capabilities that traditional Java profilers just don't have, with the exception of Solaris Studio. And it has a low overhead and no save point bias. What do we lose? For starters, we lose a register because we have to preserve the frame pointer to allow perf to walk the stack, which means for certain applications this is going to be an overhead. For most applications it's probably not going to show up. We lose interpreter frames because the interpreter is its own little program as far as perf is concerned. It's not a real frame from perf's point of view, so when you look at methods that are in the interpreter, you will just see interpreter. On occasion, you'll get broken stacks, so perf will fail to walk the stack at some point. It'll give you something, but you might need to massage it a little bit to get the data you want. And on all the kernels, it has a limited stack depth. With the more recent releases, you can open this up to as much as you like. Finally, it just gives you a lot of information to look at. And we'll be looking at profiles for the remainder of this talk, and we can try and make sense of that. This is what it looks like. So I said the colors don't mean anything. Initially, they don't, because it was all a fully native application. What we see here is we have C++ code that's going to be yellow. Typically, this will be the JVM code. We'll see the GC code will be yellow, and some of the JNI libraries we might call into. We see the native code is red, and the kernel code is orange. And finally, we have Java code. And we have two kinds of Java code here. We have real frames, which are the code blobs that the compiler generates, which are an amalgamation of all the code that's been inlined into them and the good stuff that the JVM generated, and a whole lot of cooking goes into code blobs, really. And then we have inline methods that are not actually there. They're just metadata about the particular locations in the real code blob. The distinction is important for two reasons. One is we want to look at something that we wrote, right? We wrote with methods that got inline, and we want to see the methods that we wrote and the stack that we expect. The other reason you want to see them on your stack, because if you didn't, you wouldn't get a very stable profile, because from run to run, the inlining decisions can change. And finally, in the context of profiling, inline methods are a bit of a lie. They're a bit of a fudge. They are only there to help your mental model, but in reality, the compiler can reorder your code and eliminate large chunks of code. And the cost model that you have in your head looking at code just completely goes away when the compiler is done with the code. So it's helpful to have the inline metadata, and it can be correct, or at least in the right direction. It can also be very, very misleading. Part of the problem is because you inline a lot of code into one method, if the profiler misses by a few instructions, you might end up in a very different place in your code base. So you're looking at line 100 in your class, and the problem might be in some previous code line, that it's in a completely different class that's just been inline and mangled and moved around. So while this is a problem for all profiles, I think this is the first time, at least for me, that I've seen a profiler that can give you an indication of whether or not the method you're looking at in your profile is an inline method or a real method. And the distinction can be important. Right, so now we're going to look at some Java profiles here. I'm going to start from the start. And this is a benchmark. And some people will tell you benchmarks are evil, but we're still going to look at benchmarks, so fuck them. Right, it's a benchmark for a JSON library, and we can only see the Java portion. This is what it would look like in a typical profiler of the async get call trace kind. And we start with this, and if we start to interpret this profile with this new visualization, one thing we can see is that the JVM inlines a hell of a lot. There's this method JSON write a string that is, it's got quite a wide chunk of itself. It seems to spend a lot of time getting chars out of strings, which seems reasonable for a JSON method. We can see some inlining behavior here that is quite curious, so we can click on it and open up the view a bit. The reason I say it's interesting is because you can see that the write method here is a real method. Okay, it inlines one method in, and then inlining stops, and we have 3 real methods here. If it's a really hot method, maybe inlining should happen more. There's a bit of a hint to why it didn't inline here, and we can see that we have different write methods that we call to from this method. This is what a megamorphic call site looks like. A megamorphic call site is a call site where there's more than one implementer of the method that you call into. So the JVM can't inline that call. It will inline if there's only one implementation, or if even there's only one implementation in that call site. It will do that through interfaces as well. If there's 2 implementations, it'll stick an if statement there and do the right thing. But if there's more than 2, you'll end up with something that looks like this, which is a megamorphic call site. And that means overhead, that means lost opportunities in terms of optimizations. So maybe, if this was our code, we would go in and try and strip away that problem. Okay, so we look at this problem, we look at this program, and we might think we should definitely go and optimize part of the Java code here. Maybe there's good optimizations to be had, some good opportunities. But this is still not the full scope of what's happening. This is a slightly better idea. This is the same code, but now with the runtime stubs actually factored in. And you may think, okay, how much array copying do I actually ever do? And it's scattered everywhere. There's an array copy here and an array copy here, and we can actually look for it and see how much it adds up to. So in this particular case, sadly it shows up at the bottom, there's 17% of the profile that just would have been swept under the rug by Java Mission Control and similar profilers. Okay. This is potentially a big problem for us. Okay, if you're looking at your application, I will say this again, you're probably not seeing some array copying. There's a good reason why array copies are optimized. Another thing that we can see here, going back to that same method that didn't get the inlining we wanted. Where is it? Over here. We see these guys. Okay, we see, we see the iTable stub and the vTable stub. Now there's a reason why megamorphic call sites and virtual calls are expensive, and that's part of that reason. Not only can you not inline, you also need to do a lookup of who is the right implementer, who should I call in this instance, and that comes at a cost. And that cost, again, is something that is missing from your typical profiler. How much does it cost you is a question we can answer with the search again. So if we look for table, we'll see there's another 7%. So altogether, we're looking at like a quarter of this profile was hidden from us. In your even your better Java profiler would still fail to show you this because it fails to show runtime stubs. Now, there's one more thing I wanted to show. Is it on the next slide? Yeah. Another thing that's nice about this, when you get the extra visibility here, is that sometimes you just happen to come across something you didn't know. And in this case, I didn't know it, at the very least, that if you use reflection to work with your arrays, you actually end up going to JNI. So we have reflect array get here, and you end up calling into a JNI method that ends up accessing the array. Obviously, that can't be very optimal. And again, perhaps if you see it in your application, this is something you want to optimize. We'll look at a few more Java profiles. This is a netty benchmark. We're not going to analyze it in any way, but I'm showing this to show that in many cases, your code calls into a part of the OS. In this case, netty is calling the ePOL selector. It's calling the it's writing into sockets and reading from sockets. If you're looking at your Java code and you're actually ending up in native code, there's not that much you can do for your Java code to optimize it if all the time is spent elsewhere. But for some people, in particular, if you're Norman Maurer and you're writing netty, you can pick a different OS interaction, perhaps, and get more mileage. And this can become valuable for you. In this particular case, Norman has implemented his own sort of native ePOL JNI library to work around the limitations in OpenJDK. So again, if you have interactions with JNI, this can help you see further. And finally, this is a particularity of the JVisual VM profiler family. Because they show you all the threads, they show you the thread states, and they show you threads that are in unsafe park as runnable, which is quite annoying because obviously if they're parked, then they're not runnable. But what about the cost of park and unpark? When I park a thread, I also pay a few CPU cycles. There's absolutely no way for you to differentiate the two if I call it runnable when it's both running and not running. So here we can see that this is a profile for Cassandra. And in this case, Cassandra's spending a fair chunk of its time parking and unparking threads. So if you see this in your application, perhaps you should tune your thread pools because you're mostly putting them to sleep and getting them back again. Maybe the thread pool is too large and you're just rotating through them in an inefficient manner. I think that's pretty much it for the Java portion. Yeah. Okay. So what did you see? Just quickly working through it, we saw the data that we get from inlining. We saw some runtime stubs, calls into native, and the costs of park, all of which become evident in these profiles. We can get more out of this if we spend some time on the text files and improving them and massaging the data. So we can post-process, say, all the Java threads that have the same initial to look the same, so we can get our thread pools separated and named for our applications. If we're not interested in what actually ends up happening in the native code, we want a more compact image to look at, we can trim the calls into native to just the first call. We can collect the broken frames into one location, which will make it easier for us to look at this. Yeah, we can color the JDK and framework code, which would be just helpful in finding our code in the whole mess and differentiating the cost when it goes into JDK, netty, Spring, or whatever. And now we'll go a bit further. So just now, we were looking at this profile. And we were wondering, what can we do for the Java portion here? And once you take a step back and look at the CPU for the whole process, not just the Java threads, you realize that your problem in this benchmark is actually not the Java code at all. It's the GC threads. The GC threads over here are taking up 25% of the time. We can actually get more out of this if we search and we see, yes, it's 26%. So I was talking about post-processing. One thing that would make sense is collecting all the stacks from the Java threads into one side and all the JVM threads into another pool and present that as a sort of unified profile. This is something that you can easily do by disabling the thread ID collection, then it'll happen naturally. The reason I turn on the thread ID is because of broken stacks, and at least you know that the broken stacks came from Java code. When you have the thread ID, this is something that can certainly be improved on. The other thing, and that's a shame that profilers don't give you this more readily, we know how many samples we wanted, right? We wanted 100, in this case, 100 samples per second, and we profiled for 10 seconds. So if this thread was working at 100%, it should have 1,000 samples. It's the way cycle profiling works in this instance. So we know this thread is not getting fully utilized. We also know that these threads are doing young collection because we can look at what they do. And that brings me to difficulty with profilers just generally. When you look at multi-threaded code, it's often hard to say this bit of the profile is actually blocked by something else, and therefore if I improve this, this will improve as a result. So it takes a bit of familiarity with the profiles to understand that, and in this case, if you keep in mind that the GC threads are going to be blocking your thread from doing any work while they work, it sort of adds up. The other thing to realize about these profiles is that the number of actual samples is going to depend on the number of cores on your system and the amount of utilization. When you ask for 100 samples per second, that's 100 samples per CPU second. So if you have 20 cores, you can actually use 20 seconds of CPU in 1 second, and therefore get 2,000 samples rather than the 100 you might have been expecting. But with those pieces of data, we can start to visualize utilization actually as part of our profiles, which could be quite handy and interesting. Right. Now, this profile is the same profile. It looks completely different. The reason it looks completely different is because in this profile, we're profiling the benchmark while it's being profiled by an instrumenting profiler. There were a lot of profilers in that sentence. So I took the benchmark, I hooked up JVisual and I pressed that button that says profile in the instrumenting profiler tab. Okay, and what happens is it completely shafted my little program here, because the program is now, as we can see, mostly gone back to the interpreter. What happens when you use an instrumenting profiler is that it injects a lot of timestamps into your code, and now your code is new to the JVM. It's not the hot code that it used to have, it's completely new code. It has to recompile everything. It has to wait for it to become hot to recompile it. Okay, and it has to run the compiler threads. So we can see here, these two big boys are the compiler threads eating up our CPU. The reason there's two of them is JVM ergonomics. I have 4 cores, then I'll have, by default, 2 compiler threads. They're working concurrently as fast as they can to make this happen. Another interesting thing we can see here is that actually, once I've instrumented my code, I'm actually spending like 10% of my time calling get time. It's a classic sort of management problem. how much time do you need to spend reporting to your manager about the work that you're doing, and are you reporting the time in which you're reporting as reporting time? And usually you don't. You just do less work and write more forms, which is the case here. So obviously using the instrumenting profiler comes at a cost, and it comes at a cost of a lot of compiler effort, and it comes at a cost of just changing your code to the point where it's a lot less performant than it was before. What happens when we use the sampling profiler? Well, funny enough, and this is, I don't know if you, maybe I've been looking at these slides a bit too much. The profile for the code looks the same. It looks the same as it did initially. And this is where your eye as a human being gets to grips with the shape of it. And you can say, well, it's sort of the same. It's very different from what the instrumenting profiler did to it, which completely changed it, right? But it's getting a lot less time to run. Okay, it's only 30% of my profile here. And the reason is not that obvious, because if we look for the amount of CPU we spend on get stack trace here, it's not that expensive to collect the stacks. The problem really is that I have to stop the thread from running every time I collect the stack. So the cost of suspension and reanimation are what's killing me here. So that's what happens when you profile using a sampling profiler. So there we go. Okay. Sorry. Okay. So we looked at a bit of a meta profile. We looked at JVM threads. JVM threads can inform you on, at the very least, CPU utilization. Getting the CPU utilization out of JVM threads can be a bit tricky and not something most profilers report to you. So it's, if you ever wondered how much time am I spending in my GC and you had to correlate your CPU profiler with your GC log, it's quite nice to just see the CPU utilization from the profile. You can get a bit of an insight about what the GC is doing. You can look through the stack and look it up online. It's all open source. If you like that sort of investigative reading, you can do that. And you have to contend with the fact that the JVM is a concurrent program. You have to contend with the fact that there's multi-threading that works, and that can be quite confusing. I can't really offer you much comfort on that just yet. There's a lot more we can do with this tool. We can do machine level profiles. We can do cluster level profiles. Because it's just a text file, you can just pile more profiles together and generate one flame graph for a whole cluster of, say, Cassandra machines, and just get an idea of how they behave as a cluster. And there's tons of perf features that we haven't touched on that you can use to generate these profiles. So the default profile is using cycles as the metric you're interested in, but you can use cache misses, you can use page faults, you can use whatever you like. And finally, I would like to encourage everyone to just dive in and try their hand. So just to throw a few ideas, you can reintroduce the self percentage and color the graphs by self percent for each method. I tried that. It's quite ugly, but it's a nice little project. You can try and add core utilization indicators. So you can color different threads by the number of samples versus the number of expected samples, and I think that would be quite an interesting little exercise. There's multi-threaded profiles. They require a bit more knowledge about what kind of threads you expect, but I think you can definitely group threads by the root stack and try and get some views from that. And you can enrich the Java profile with metadata you collect from elsewhere. One of the things Mark Price, who I can't remember where he works now, used to work for LMAX, he did a little script that collects all the Java thread names and pulls them in, and then instead of seeing just the thread IDs, you get to see Java thread names, and you can use that certainly a bit more to do grouping. In summary, there's new tools here. There's a new tool chain. There's bits and pieces here for you to dive in and use, and also tweak and hack and share and just get into the whole game. You can profile at a wider scope, not only at the, you get to see more, but you're exposed to more and more new stuff, which is an opportunity to learn more stuff. And just enjoy it as a way to explore your systems. Thank you very much for listening. And yeah, does anybody have questions?
So one of the big problems that I have whenever I'm trying to profile anything that requires a call stack is the cost of acquiring and building the whole call stack from the JVM. So I assume the perf way of gathering that information doesn't have as much overhead.
So it's walking the stack for perf is relatively cheap. I can't back it with numbers, but it's as far as I can tell, it should be cheaper than what async at call trace does, because it doesn't collect any metadata. While doing it, it's just walking the stack, collecting the addresses. But the trade-off is that you have to have a frame pointer to do this, and if your stack is very deep and your methods are very small, so you end up with a lot of calls, you will pay for that call overhead. And you will pay for the extra prologue and epilogue for each method. So it's worth trying out and seeing how it impacts your system. But it should give you a different result at the very least.
And the quick follow-up: does that frame pointer flag help the standard tooling gather stack traces faster? I mean, does it switch to like a fast walk or anything?
I don't think the standard tooling capitalizes on it. So, anybody else? All right. Thank you for listening.